Hi, my name is Keith Scott. I'm going to be presenting a tool that I put together to do container-based emulation of networks with time-variant connectivity. Container-based emulation works by using lightweight Docker containers to emulate the various nodes in a network. So here we've got the network that we want to emulate up at the top. So we've got 3 routers and some nodes at each end, and they're just connected, in this case, by simple point-to-point links. So what the container-based emulation does is it uses a Python script and an API into the Docker infrastructure to read a scenario file that describes the network topology, the time variant connectivity, and then configuration information for all of the nodes, and then makes calls into the Docker API to instantiate the right set of containers and Docker networks and connect them all together in the right way to manage that. And then it follows the timeline of the time variant topology description and modifies the connectivity of the various nodes into the Docker networks so that it imposes the link constraints that are expressed in the time variant topology file. There's also this monitoring stack that's sitting off to the left. The monitoring stack's job is to provide a way for nodes to log information that you might want to display in something like Grafana, and I'll show some examples of that coming up. So what do we mean by time variant connectivity in a network? Here, this slide is showing a network of 3 nodes, A, B, and C, over at the left, with some connectivity between them. And then off to the right is essentially a timeline showing what that connectivity looks like as a function of time. So if you follow the top timeline, the timeline for the connectivity between nodes A and B, between 0 and 120 seconds, they're bidirectionally connected with low latency. Then they're disconnected between 120 and 180 seconds, bidirectionally connected again with low latency between 180 and 240, and so on. And then on the bottom, between nodes B and node C, there's bidirectional connectivity between them for 0 to 60 seconds. Then they're disconnected until 120, connected from 120 to 180, and so on. So what this does obviously is it builds a network where for the first 60 seconds you've got connectivity all the way through, and after that you never have end-to-end connectivity. You've only ever got connectivity from one of the end nodes into the middle. OpenNetEm has a number of ways that you can build those connectivity files, ways to express the changes in connectivity. In OpenNetEm, you can express the time variant topology in a number of ways. You can use Excel files, CSV files, and JSON files. But the idea is always the same, right? You express the changes in the connectivity in the network at a specific set of times, and then the master Python script that is running the emulation is responsible for reading that, tracking the times, and then imposing the various sets of constraints onto the links according to the topology file. And what it's doing for that is it's using Linux advanced routing and traffic control, and in particular the NetEm QDisk for the TC module. So anything that you can do in NetEm, you can do from here. We've implemented delays, obviously, and link rate constraints between the nodes. Okay, how do we put all that together to describe not just the time variant connectivity, but also the network topology, the configurations of the various nodes, and the commands that we want to run while we're executing the emulation? So the scenario files look sort of like this. They're JSON files. There's a test name, a place to put some metadata. The start delta, there are ways to delay the sort of the 0 time of the emulation in order to let the nodes get set up and settle before that starts. So for instance, especially if you want to start Ion, you want to give it some time for all the various Ion daemons to start up and get running. And then here, specifying the topology file name is specifying this Excel spreadsheet and sheet 1 within the workbook as the description of the time variant topology. And then after that, we get into what are the networks that are in here. So the networks are named. The names are pretty arbitrary, but generally, if I have like node A and node B connected by a network, I'll name the network AB. And here, I'm actually supplying the IP addresses of all of the connections into the networks. If you don't want to do that, it will, in fact, if you don't provide that information, opennetem will auto number the networks for you. I do this so that I know exactly what all of the interfaces are named and what their addresses are, so that when I write the commands later, I've got a little bit finer grained control over what's going on. The node configuration section portion of the scenario file is where you define the various nodes and what their capabilities are. The most important part of this is probably the container image. So that's telling you which one of the Docker images you're going to run in order to instantiate that node. And then there's other information in here that talks about the node and the interfaces onto the various networks. So here it's got node A showing that it's going to be running the NetEm ION container image, and it's going to have an interface onto the address which we called AB above in the network configuration portion. And the address on that network is going to be 10.44.3.1. The mount points define directories that are bind mounted from the host down into the node. So here we're bind mounting mounts / node A into NetEm mounts node A. And what that does is by bind mounting a directory from the host into the node, it makes all the files that are in that directory available to the Docker container that's running. And anything that the Docker container writes to those directories then gets written back into the host. So that's a way of storing data persistently during the emulation. Otherwise, if you just write inside the container, if you just write data to some directory that's not bind mounted outside, that data will not persist once that container is destroyed. And then there's a working directory that sets where the working directory is inside that node, and that's useful for when we get to running commands later. There's also this global mounts up at the top, which defines a directory that gets mounted into all of the nodes. So a lot of times you want to have some utility functions, some utility programs that you're running, and you want those to be available to everybody, and you don't necessarily want to copy those into every one of the bind-mounted directories. So the global directory gives you a good place to put stuff like that. The command section of the scenario file gives you a way to specify commands that are run at certain times during the emulation. So there are some negative times in here. Again, the emulation is set up so that you may want to give things time to get set up and settle. So here at time -10, we're starting up ION on all of the nodes. And then we've got 10 seconds before time 0 of the emulation for all of that stuff to get set up and to settle. Similarly, at time -2, we start BP echo, and we redirect that into a file so that we can see what's coming out of BP echo there. In the commands, there are a couple things that you can use. NetEm node name gets replaced by the name of the node on which the command is run, which is useful when you're running the command on multiple nodes, as you can see on the top line there. Start time gets replaced by the start time, which is second since the epoch. And then you can use NetEm adder and then a node name and a network name to go and get the address of a particular node on a given network. You can have as many of these commands as you want, and as you can see, you can do things like redirection works. You can start up TCP dumps. You can do all the normal kinds of things that you would want to do. And the purpose here is if you've got an emulation that you want to run for like a particular fully canned scenario, you can stitch up all the commands, run the emulation. It dumps all of the data, and then you can post-process that later. You can also run this in a way where you use opennetem just to set up and configure the network, and then you can use Docker exec to get into the various containers and play around on your own. So now I'm going to run through two of the tests that come with opennetem. The first one doesn't use ION. It just exercises the time variant connectivity and uses some of the monitoring stack so that we can actually get a look at what the round trip times are between nodes. So test one is actually has 3 nodes, but here we're only interested in A and B. There's a C node that's sitting off beyond B. And here we're showing sort of what that time variant connectivity looks like. So for the first 30 seconds, A and B are connected with decent data rates and very low latency. Between 30 and 60 seconds, we up the latency between A and B to 3 seconds and B to A to 4 seconds. All of the links are individually configurable in each direction, so we get a 7-second round trip time there. And then we disconnect the network for the next 30 seconds. Between 60 and 90 seconds, there's no connectivity from A to B. And then at 90 seconds, things come back with a 2.5-second round trip. And then finally, between 120 and 150 seconds, we drop down to a 1-second round trip time. So we'll run this, and then we'll look at the data that comes back via Grafana and the monitoring stack, and also look at some of the files that get generated by node A in response to the commands. Here we are. I have everything set up on this machine here, and I'm in the test1 directory, so I'm going to go here and invoke the netem scenario.py master script on test1 scenario. So it fires off, spits out a lot of diagnostic information at the moment, and it's also set up to wait. One of the things that you can do is cause it to wait until a minute boundary in order to start the emulation, because a lot of times you have things that are timed for 30, this happens for 30 seconds or a minute, and it's nice to have those in Grafana come out right on the minute boundaries. So it's going to wait here until the minute. All right, so here now it started executing commands out of the command file, and it's logging the latency between node A and B through Prometheus and into Grafana. Here, the latency is quite small. Things start out fully connected with no latency, no additional latency, so we're seeing a couple of milliseconds round trip time. And when we get out to 30 seconds, we'll see that that time jump up. So now we see that the round trip time has jumped up to 7,000 milliseconds or 7 seconds. So we're going along here. There are some little artifacts that come like that little jump there to 10 seconds. With the changes in topology, sometimes the Linux ARP tables time out and get upset, and then you have to ARP again, and that'll cause a longer RTT while that happens. So now we've gone past 90 seconds, and the network was disconnected, and then reconnected back here with a lower round trip time of 2.5 seconds, as we can see in the plot. And then eventually it drops back down to 1 second. So once the test is over, we can look at some of the data that got written down into the bind mounted directories by node A. And there are sort of 3 interesting things here. There's an A to B round trip time file that is the raw output of A trying to ping node B. There's a ping monitor.out file, which is an enhanced sort of JSON formatted file that contains the same information from the A to B RTT text file, but it's more suitable for then jamming into the Prometheus database and showing it on Grafana. And just sort of as an example, some of the commands that we issued by node A during the emulation caused it to take a packet capture. So we've actually got a PCAP of what was going on, and we can go back and look at that and see what's happening. And because node A wrote those into the directory that was bind mounted from the host, all of those files persist once the node A container is destroyed. Okay, great. So how do we actually run Ion in this thing? There's a different Docker image that contains the Ion code, and in test 3, there's a set of subdirectories that get bind mounted in the nodes that have all the right configuration files to build a network of ion nodes that are configured to talk to each other. We use a couple of commands, one that starts all of the ion nodes sort of before time zero in the emulation, and then a second one that installs the global contacts file. The issue there is trying to make sure that the contact file and the times in it are actually synchronized among all the nodes in the emulation. And this does pretty well. It tends to synchronize certainly sub-second, and usually down to a couple tens of milliseconds. So this shows the time variant topology for the network. We've got a linear 3-node network. We're running an LTP convergence layer between nodes A and B and a TCP convergence layer between nodes B and C. For the first minute, everything is connected, and then after that, things are connected only on one of the links. So between time 60 and 120, node A is connected to node B, but B is not connected to C. And between 120 and 180, B is connected to C, but A is not connected to B, and things go on like that until we get out to 570 seconds. So I'll run this and then talk about some of the output from the utility applications that analyze the output of the bping command, so that we can see that Ion is in fact getting all of the pings through, even though we don't have end-to-end connectivity anytime between 60 seconds and 540 seconds. So the main command that the test3 scenario runs is a bping from node A to node C. And this is showing just a chunk of the raw bping output from that. So you can see the sequence numbers coming back. This is node probably 1.3 pinging node 3.1 with a BP echo running. So you can see these coming with the round trip times over at the right, which are relatively small when they start. You get a bunch of A characters because I had watch characters turned on, and bping ended up printing the watch characters out, but that's fine. And then you can see a huge jump to a 60-second round trip time after the disconnection and then the reconnection, when bundles can finally make it back. And then those round trip times go down slightly as we receive those bundles, because when things are connected, the round trip times are low. So the round trip time actually goes down by a second with each new bundle that comes in. And then down at the bottom, I just clipped out part of the file and showed another chunk down later, just to illustrate that sometimes those responses do in fact come back out of order. So the cool thing about Ion is, of course, that you can in fact communicate over these disconnected networks. It's kind of hard to figure that out from the raw bping output file. You can, in fact, go through and by hand look at all of the sequence numbers and figure out that Ion did, in fact, deliver everything. But there's a little analysis program that I wrote that will parse the bping.out file and tell you some stuff about it. And this is what it spits out. So you can see here, we had a minimum sequence number of 0, the maximum sequence number of 562. So we saw a total of 563 responses. They were all unique. And then it's got the round trip time statistics down at the bottom. So that's pretty cool, because it says that we were able to run bping across this network where for most of the time we never had end-to-end connectivity, and yet by the end we had gotten the answers to all of the bundles we sent. So that's cool. We can define these networks with various topologies and time variant connectivity, and we can run Ion in them. If you've ever actually tried to set up and configure Ion, you'll know that getting all the configuration files into a consistent and working state can be a bit of a challenge. OpenNetEm provides some extensions to the scenario file format that will allow it to auto-generate a set of basic Ion configuration files for you, and then you can go and tune those up the way you'd like. So there's extra stanzas that you can put down in the scenario, in the node configuration, that add things like, what's the node number that you want this thing to use? What are the out ducts that you want this node to have, and on which interfaces? OpenNetEm will generate you a working set of ION configs, put those into a directory that you tell it to, and then you can turn off the auto configuration, use those configuration files that got generated, and tweak them the way that you want if you want to do things on a more granular level. And this just shows a chunk of the test-free scenario config file where we've actually set things like the ION node number, set up the out ducts, and where we want the config files to get written. There is documentation for all of this. If you type make HTML in the doc directory in the repository, it'll build you a bunch of HTML documentation. There's also, for setup, there's an all setup.sh script at the top level of the repository that will set everything up. It'll build the Python virtual environment. It will make you the HTML documentation. It'll build the Docker images, and it'll set up the database and dashboard configurations and start the monitoring stack. So I'm still actively adding functionality to this, but one thing that is probably high on my list is the ability to set up containers to accept port forwards from the host. This is a standard Docker thing where you can forward ports from the host into the containers so that you can, for instance, run a web server inside of a container and connect to it from outside the host. So what I'm going to look to do is be able to configure the ports for like 4556 so that the various CLAs for ION can get forwarded into a container, and that way you can have an emulated network that might have tens or hundreds of nodes internally and connect it out to something like the project working group's test network so that we can build things out that way. Thanks. I hope you find this useful. Here's the GitHub repo from which you can download the opennetem software, and feel free to contact me if you've got any questions. Good day.